Hello everyone, welcome to my presentation. This is John work with Yu Wan. Alright, let's start by defining a few things. The input is a set P of points, multidimensional points. And we will also need the dominance relationship. As usual, a point dominates another if the coordinate of P is at least that of Q on every single dimension. Every point in the input is associated with a label. So every label is binary. It can be either 0 or 1. A classifier is simply a function that assigns a label to every point in the d-dimensional space. And in particular, a classifier is called a monotone classifier if it satisfies the condition that you can see here. So essentially, if you think about P is here, and if P has the label 1, and then everything on its top upper right corner will have to receive a label 1. Okay. Conversely, if this P has label 0, and then everything in its lower left corner will have to receive label 0. All right, now suppose you have fixed a classifier. We get to talk about the error of the classifier on the input P. The error is defined as essentially the number of points that are mispredicted by the classifier. In this talk, we're going to focus on monotone classifiers. You can, or conceptually, you can enumerate all the monotone classifiers. And then for every classifier, you can calculate the error as I just defined. And then you get to say what is the smallest error of all possible monotone classifiers. So that is the symbol K star here. Here, this example is two-dimensional, and you can see 16 points there. For your convenience, I have colored the points. The black points have label 1, and the white points have label 0. Okay. The red curve here represents a monotone classifier. So you can imagine everything that is above the red curve is classified as 1, and everything below it is classified as 0. Okay. And what's the error of this monotone classifier? Well, you can see that it misclassifies P11, right? So this is supposed to be 1, but it's white, which means label 0. And also it misclassifies P15, and there's another point misclassified here, P1, and therefore the error of this classifier is 3. Okay. All right, now let's define the first problem studied in this paper, and this is called active monotone classification. All right, so think about the input I just defined. In the beginning, the labels of all the points are hidden from you. Well, you can design an algorithm to probe any point you like. Okay, so when you probe a point, an oracle reveals the label to you. Okay, well, in the end, your algorithm will have to output a monotone classifier, and then we can evaluate the error of this classifier to see how well your algorithm has done. Okay. So the cost of the algorithm is defined as the number of points probed, right? So we want to find a classifier that is as accurate as possible. Well, obviously, you cannot do better than K star, right? And very naturally, we say that a classifier is 1 plus epsilon approximate if its error is at least at most 1 plus epsilon times K star, as you can see here. Okay. So the first problem statement is here. Okay, so you want to find a 1 plus epsilon approximate classifier, and you want to probe as few points as possible. Right? All right, so let's define the second problem. This is the passive counterpart of the problem. Well, the problem definition is very simple. So the labels of all the points are revealed to you directly. Okay, and this time your objective is to find an optimal monotone classifier. Okay, so you have to achieve the optimal error K star. Okay, And this time the challenge is to minimize the CPU time. Okay, now we're going to talk about the previous results on the two problems. One parameter we have to mention here is the so-called dominance width of the input set of points. Well, specifically, this is the number of points that you can take, the maximum number of points you can take from the input set without having 2 points dominating each other. Okay, so for instance, in this example, the dominance width is 6. Okay, so it's 6 here because you are able to pick, let's say, P10, 11, 12, 13, 14, and 16. You can pick these guys. No 2 points have this dominance relationship. All right, now let's talk about the previous results on problem 1, starting with the upper bounds. Right. So one way to do it is to use the A-square algorithm. So this is a famous algorithm from active learning. Okay, and in our context, if you want to achieve this approximation ratio 1 plus epsilon, by the way, this is a randomized algorithm, and it's able to achieve this approximation ratio with high probability. And then you are able, and then the cost, the number of points that you have to probe, is given by this. Okay, so this is theta here. It's a so-called disagreement coefficient of the input set. Okay, and this lambda here is the VC dimension. And we don't have to worry about the concrete definitions of theta and lambda. Okay, but it is already known that in the worst case, both parameters can go up to W. Okay, at least W. So in other words, the best possible claim that you can put on A square in this case is W squared over epsilon squared. Well, in pods 18, so that was 4 years ago, there was a paper proposing a very simple algorithm. And the algorithm is able to achieve an approximation ratio of 2 in expectation. And the cost is essentially just W. All right, the same paper also provides a lower bound. Okay, it shows that for any constant approximation ratio, okay, for any constant approximation ratio, you have to probe at least this much. Okay, essentially this is roughly W. All right, so let's turn attention to problem 2. So basically not much is known about this problem, except that the problem is decidable. Okay. All right, so the first result we have in this paper is that we give you a new way to achieve 1 plus epsilon approximation ratio. And the cost you pay is W over epsilon squared and multiplied by a polylaw factor. Well, as a corollary, the algorithm can achieve any constant approximation ratio in expectation, and the corresponding cost is just W, and with a multiplicative polylaw factor. Okay, so if you compare this to the lower bound obtained in 2018, you can see that this algorithm here is tight only up to a polylaw factor. Okay. All right, so how about problem 2? So we show that problem 2 can be solved in polynomial time, and this is polynomial to both the dimensionality D and N. All right, so I don't have much time left. In the rest of the talk, I'm going to give you one slide for each problem. All right, let's talk about problem 1 first. Okay, one obstacle in this problem is that you should not hope to be able to estimate the error of every classifier up to relative error epsilon. Now the thing is, you cannot estimate error h up to relative error, and you want to have a relative error guarantee, right? So how to achieve the purpose? So that is the challenge. All right. So in this case, let's just focus on one-dimensional space, and let's say we have n points. Now remember, in one-dimensional space, every point is just a real value, right? So we've got n real values here in ascending order, right? Well, now suppose that we know there are only 2 possible scenarios, all right? So in the first scenario, all these points have label 1, okay? Now in the second scenario, there's only 1, 0, all right? So all the points have label 1, but there's only 1, 0, all right? So 1 point is 0, and this point cannot be P1. The point will have to be one of these n-1 points from P2 to Pn, all right? But only 1. All right, now let's consider a very, very special classifier that simply predicts all the labels to be 1. Right? So this classifier has error 0, in the first scenario. Okay, and in the second scenario, it mispredicts the only point with the label 0. So that's why its error is 1. Okay. Well, it turns out that since you are not able to estimate the error of H true up to relative error, if you were, let's say you set epsilon to be something less than 0.5, let's say 0.49, and then you will be able to precisely know what is the error, because you see in the first scenario it's 0, in the second scenario it's 1, right? So if you achieve an error of 49%, and then you will be able to distinguish these two scenarios. Well, unfortunately, we already know that it's impossible to distinguish the two scenarios unless you want to probe n points, right? So immediately you hit a dead end here. So how do you even proceed, right? All right, so let me tell you how to proceed. You don't have to distinguish the two scenarios. If you already know that these are the only two possible scenarios, you don't have to probe anything at all. You just return H true, all right? So of course, this is only a toy scenario. This is only a toy situation. And what is non-trivial is to do something like this for any data. All right, so let's very briefly talk about problem 2. This problem can be reduced to the max flow problem, right? So the classical max flow graph problem. And interestingly, once you have found an optimal flow, right, the maximum flow on this graph, you are able to construct a monotone classifier, which turns out to be optimal. All right. So okay. So with that, I conclude my presentation. Thank you very much for your attention. See if I can take any questions.